Hello. This lecture will cover pages 79 through 84 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Operational Amplifiers, Chapter 4G, Designing Linear Equations with Op Amps. We're going to start on page 79, and before we get into the main part of the lecture, I want to mention some other Op Amp circuit configurations here. If you notice, we have a configuration for a summing inverter. Basically, this configuration of resistors will give you an output that is a summing inverter. Notice basically what it does is it sums up the voltages, gives you a negative total gain, and each voltages have a separate gain associated with them. Now, you can come up with these equations I'm going to show you here in a minute. We're not going to do that, but doing an analysis at the virtual ground node here, doing an analysis at the virtual ground node here, and doing an analysis at this point once you project this voltage divider rule here back to that point, you can come up with all these equations. But if you recognize the circuit configurations that look like this, and it's basically circuits that we've had, you can go straight to this equation. A lot of engineers, when they see they need this type of equation, they'll go straight to that circuit. So you're going to have a homework problem associated with this summing inverter. It's problem 436 on page 167 of my textbook. And it's basically this right here. This is the problem that you're going to work for me. It says determine the expression for the output voltage V out of the inverting summer circuit as shown. So you are going to go through the nodal analysis on this problem to get that for homework. You'll do that once and you won't have to worry about that again. A dual inverted summer with gain. Well, if you take a look here, basically they're showing you a configuration that'll give you a dual summer with gain. And they give you a value of resistance R, and they keep this value of this resistance 10 times this value. They're both R, so it gives you a gain. Notice it's a inverting amplifier circuit. And basically it sums up these voltages, and it gives you a gain of minus 10. This divided by this, or this divided by this on each one of these. And then finally, a differencing amplifier with gain. They work out the equation. Here, if you take a look, we have VA going into the non-inverting input, and we have VB going into the inverting input. This value resistance is the same as this, and this is the same as that one. And the output expression is the difference of the voltage, VA minus VB, times a gain factor of this divided by this resistance. And you can see example 4.5 on page 158. They actually work this problem out. I don't think we have a homework problem like that, but basically if you take a look at this, this is the analysis of it. It's in your textbook. There's the circuit. And I'm sure you can all do this by now. Basically, take the voltage at this point here, which is V1, which is V2, and use a voltage divider to find what proportion of V2 is at that point. V plus input. It's V2 times R4 divided by R3 plus R4. Project that back to this point and do your nodal analysis at that point. And you get these equations here. And if you follow down through there, there's the analysis of it. So if you recognize these circuits, and you can use them. On page number 80, we talked about this before, using superposition to solve operational amplifier circuits. I want you to look in your book at some of the field engineering exam problems on page 169. Like I said, we've done this before, and I want you to just take a minute and go through these three problems right here. I want you to use superposition on this particular circuit here and tell me what the answer for V out is. Remember what superposition told us. We're going to get to it in the next chapter, but basically it says you can treat these individually by reducing the other source to zero, and you'll find out the way you reduce voltage sources to zero so they have no effect is you short them. So the first thing you do is take this 4 volts and you short this one and ignore it. You short it to ground and you get the gain output. We're going to call that V out prime. And you note that. And then you go back here and you short this one and you see the result of this minus 2 volts. And you get the gain output, you get the voltage output for it. We're going to call that V out double prime. And then you algebraically add up your V prime and V out prime and V out double prime, and you should be able to analyze this circuit right here. And in this case right here, I want you to go ahead and see what the value of R2 would be. Basically, using that superposition approach by substituting each one of these values in. Do the same thing down here. Using superposition, you should be able to find the output voltage. Up here, use superposition. On each of these, you should be able to find the output voltage. Let's take a look. This one here you should be able to do as well. It's not superposition. These other two problems you should be able to work out. This problem here and this problem over here. What's the voltage V out of this circuit right here? In this problem right here, what I had to do is I had to write 2 node equations, and I had to call this point V out prime. That's V out prime. You could write 2 node equations. One at node 1, I assign currents. One at node 2, I assign currents. And you could find V out. There's my solution to that problem. Again, that's a good problem too, that shows you how to use the procedure that we talked about in the last lecture. Here's a homework problem on page 81 I'm going to ask you to do. I'll talk about this in class. I'll refer to it in our weekly assignment sheet. The objective, you've been hired to do this. The objective is design an operational amplifier circuit that will find the average of 2 temperatures, T1 and T2, represented as DC voltage levels V1 and V2 as follows. V1, or temperature T1, is equal to V1, which can range from 0 to 8 volts, representing temperatures from 0 degrees to 80 degrees Celsius. And it's linear. Same thing down here for T2. T2 is going to be represented by a voltage V2, range from 0 to 8 volts, representing a temperature from 0 to 80 degrees C, and it's linear. What I'd like you to do is 3 parts to this. First, design a circuit that has a 2-stage amplifier, with the first stage summing the 2 voltages, and the second stage dividing by 2, so we can get an average. So you find the average, you sum them up and divide by 2. I'm going to divide that into 2 stages. Well, you have summing amplifiers. You know how to divide by 2. You know how to multiply by 2. It was pretty easy to pick a circuit that would do that, and pick the resistors so you can multiply by 2, a gain of 2 or a gain of 1/2. Think about that. Make that a 2-stage amplifier. The first stage is going to simply sum, and the second stage will divide the answer by 2. And that'll be the average of these temperatures. It's done every day in industry. Then I want you to design the circuit in a single stage. See if you can't do this all in one stage. Hint, look at page 79 in your lecture notes. They have a circuit that will do that, at least a part of a circuit. Then how would you modify both A and B to average 3 temperatures? You could do that with a single stage too, or 2-stage. And again, you can look back on page 79. But it's a good homework problem. Engineers do it every day, and up until this class, you probably wouldn't know how to do it, but with operational amplifiers, pretty straightforward. Page 82, which was the title of this lecture, Designing Linear Equations with Operational Amplifier Circuits. I have a number of examples here, but for some reason somebody's hired you, or you're working with a company, then you need to come up with an output that is linearly proportional to V1 and V2 inputs through this linear equation here. In other words, V out is equal to minus 5 V1 plus 3 V2. How are you going to design that equation using electronics? Well, this is the way you do it. We're going to keep all resistance values greater or equal to 2 k ohms, just so we keep our currents up a little bit, or keep our currents down a little bit so we don't have so much current in these circuits. But this is going to be a guideline we have here to keep our currents relatively small. Use superposition, treating each term independently. Well, the first thing you do in a problem like this is you have to calculate the gain for the negative slope up here, this minus 5 on the V1. So you know that the gain from voltage V1 is a minus RF over R1. So we have an infinite amount of choices here. I picked a 100 k ohm resistor up here for the feedback resistor and a 20 k here. If you take a look, the ratio of this divided by that is a minus 5. So I've taken care of that part of the expression. You always do the negative first, the negative gains first in these linear equations. It's a rule of thumb. Then you have to keep this fixed. You can't change these values when you go down here for V2. That's why you have to pick these first. This 100 k ohm stays fixed. This 20 k ohm here stays fixed. Now you get down to this point. What about V2? Well, if you look at V2, it's nothing more than a non-inverting amplifier circuit. So the gain of V2 is going to be whatever portion of that makes it to here, and then it's simply 1 plus this over this. Think about that. V2, it doesn't make it to this plus input through 1 to 1. V2 doesn't appear over here. It's a voltage divider between these two. So if you take a look, this gain of 3 on V2 has to be a product of two transfer functions. Those two transfer functions right there. The V3 over the R3 over R2 plus R3 is the proportion that makes it to here. And then this is that direct gain equation we talked about in a couple lectures ago, which is for a non-inverting amplifier circuit, which is 1 plus RF over R1, which were the fixed resistors we got up here. So all it's saying is that you need to pick, this is fixed. This is going to be fixed, this 6. Now why is that 6 going to be fixed? Because it's a gain of 100k over 20k, which is 5 plus 1. So this part of it is fixed. This is fixed because you're designing to the plus 3. That's the gain you have to get on V2. So you have to basically come up with resistors R3, R2, and R1 that give you a 0.5. In other words, it gives you half the voltage between this point and this point. That's the 0.5. That's the unknown here. Well, that was pretty easy to do because I make these resistors equal. The voltage divider says half of this makes it to there. So there's a complete design of the circuit. I have a 100 k ohm here, I have a 20 k ohm here, I have a 10 k here and a 10 k here. That's the resistors I picked, keeping them all greater than or equal to 2k, and I just designed that equation. Now you're going to have 2 homework or 3 homework problems like this, and you're going to have a lab that's going to have you do this, and then you're going to build it, and you're going to take some measurements. So you have to know how to do this. So what I done was on page 83, I say design an op amp summer to yield the following input to output relationship. V out has to be equal to a minus 10 V1 plus 5 V2, a minus 8 V3. Remember the hint I gave you. You designed for the negative gains V1 and V3 first. You designed for that minus 10 and that minus 8 first, and they're the inverting inputs. They are resistors that go into the inverting inputs. So you're going to have a circuit similar to this, but you're going to have another resistor that plows into this point here. That's going to give you your V1 and your V3. V1 and V3 are going to plow into this point here, if you think about that. And then, with those resistance values fixed, you design for gain V2. You design for the plus 5. You do the negatives first. Look back at the example number 1. You'll see that. Before you tear into this, which I left space for you to do down here, I think you ought to look at page number 84 because that might help a little bit. Example 3, here's an output expression that we want to design a circuit for. V out is equal to minus 5V1 minus 3V2 plus 4V3. Notice it's similar to what we had in the previous example 2, where 2 of the gains were minus and 1 is positive. The minus gains feed into the minus input and the plus gains feed into the plus input. Let me say that a different way. The minus gains feed into the inverting input and the plus gains voltages feed into the non-inverting input. Well, notice my V1 and V2 are negative gains, so they both come through resistors to that point right there on the inverting input side. So you have to design for R3, R1, R2, R3, R4, and R5. Design the negative gains first, the gains for V1, the minus 5, and V2, which is the minus 3. Then with those resistance values fixed, design for V3, projecting this voltage to this point, and then using the technique I showed you back here to get the gain for the plus value. The circuit looks like that. You just need to come up with the resistors, and infinite amount of possibilities there. Example number 4. Here's an equation, but in this case, a little more difficult. We have 2 plus. We have 2 plus gains, and we have 1 negative. There's your 1 negative. You could go ahead and design for that. But what about V2 and V3 gains, which are both positive? It requires another input, 2 inputs coming in. They both use the R5 in the voltage divider here. R3 uses R5 and R4 uses R5. But when you're taking into account R3, you have to be careful. When you're taking into account R3, it's not simply going to be the voltage proportion of V2 that makes it over here is not R5 over R3 plus R5. These are in parallel with one another. Remember the superposition rule where we can basically take this to ground. So if you're looking just at V2 here, think about this. Treat this value going to ground like the R5, this side of the resistor going to ground like this side of the resistor R5 is going to ground. If you see it a little better, maybe you just draw this thing over here. Maybe just draw the R4 over here like this. Maybe it's easier for you to see and get rid of it up here. And what portion of V2 makes it over here? Well, I think you can see that it's going to be R4 in parallel with R5 divided by R3 plus the R4 in parallel with R5. This is the expression for V out in terms of R1, R2, R3, R4, and R5. This is the entire expression. You just need to pick resistors that will match these values up here. Look that over and make sure you understand it. On page 84. What we just did here is, those 3 basic configurations that I gave you in previous lectures, they're pretty powerful. Those equations we come up with for gains. And if you recognize the circuits, use them. But in a lot of cases, you have to go a little bit beyond that with these op amp circuits. And I showed you some other operational amplifier circuits. I gave you a homework problem on voltage averaging. It's on page 81. I think this is going to help a lot with understanding how you can use op amps to do an engineering task out in the field. In this case, it was finding the average of two temperatures that are in two cylinders out on an oil field, or two pressures even that are out on an oil field, or the average of 3 or more. So you can display it. Make sure your process is running the way you expect it to run. And then finally, designing linear equations with operational amplifiers. Gave you 3 or 4 examples here. Some of them you're going to have to work out. And then you have a lab coming up in a number of weeks where we're actually going to do that. And that concludes the lecture.